There is a journey humanity has been dreaming about for generations, a destination we can see with our own eyes in the night sky glowing red. We call it Mars. For decades, we've been asking the same question: how do we actually get there? Because going to Mars is not about building a big rocket and lighting the engines. It's a chain of problems: distance, radiation, fuel. Some of these challenges are engineering, some are biological, and every one of them must be solved before a human ever sets foot on the red planet. This is the real story behind the question: how will we go to Mars? Right now, Mars is approximately 140 million miles away from Earth. That's the average. The actual distance changes constantly as both planets orbit the Sun at different speeds and distances. At its closest approach, Mars comes within about 34 million miles of Earth. At its farthest, the gap stretches to 250 million miles. This creates the first major constraint on any Mars mission: timing. The planets align favorably for travel roughly every 26 months. During these windows, the journey becomes significantly shorter and requires less fuel. Miss the window, and you wait another 2 years. But even during an optimal launch window, the trip takes time. Current estimates suggest a one-way journey of approximately 180 to 210 days, somewhere between 6 and 7 months. That's 6 months in deep space, far beyond the protective bubble of Earth's magnetosphere, exposed to cosmic radiation and solar particle events. 6 months in microgravity, where bones lose density and muscles atrophy. 6 months in a confined spacecraft with the same crew members, isolated from everyone else on Earth. And that's just the outbound leg. A typical Mars mission architecture includes 3 phases: the journey to Mars, the surface stay, and the return journey. The surface stay must be long because once you arrive at Mars, you can't immediately turn around and come home. The orbital mechanics don't allow it. You have to wait for the next transfer window, which means staying on Mars for approximately 500 to 600 days, more than a year and a half. Add it all together, and you're looking at a round-trip mission duration of roughly 900 days. That's 2.5 years away from Earth. So the question becomes, how do we keep humans alive and functional for that long? Before we can worry about the journey itself, we need a way to leave Earth. And that means we need a rocket, a very big rocket. The challenge here is mass. Everything you send to Mars, the spacecraft, the crew, the life support systems, the food, the water, the equipment, the return vehicle, all of it has to be launched from Earth's surface. And Earth's gravity is strong. Escaping it requires enormous amounts of energy. The rocket equation is unforgiving. For every kilogram of payload you want to send to Mars, you need many kilograms of fuel. And that fuel has mass, which means you need more fuel to lift the fuel. The numbers spiral quickly. Current estimates suggest that launching a human mission to Mars will require a vehicle capable of lifting somewhere between 50 and 100 metric tons to the Martian surface, depending on the mission architecture. That's significantly more than any rocket currently operational. Enter Starship. SpaceX's Starship is a 2-stage, fully reusable launch system designed specifically for missions like this. The vehicle consists of a super heavy booster and a Starship spacecraft stacked on top. When fully fueled and stacked, the system stands approximately 121 meters tall, taller than a football field is long, and has a mass of roughly 5,300 metric tons. The Super Heavy booster is powered by 33 Raptor engines, burning liquid methane and liquid oxygen. These engines collectively produce thrust, exceeding 73.5 meganewtons, more than twice the thrust of the Saturn V first stage that sent astronauts to the Moon. The Starship upper stage is powered by 6 additional Raptor engines, 3 optimized for sea-level operation and 3 optimized for the vacuum of space. In its baseline reusable configuration, Starship is designed to deliver between 100 and 150 metric tons to low Earth orbit. That's enough capacity to support a Mars mission, but only if the architecture is designed correctly. And that brings us to the next problem. Here's the issue. A fully fueled Starship has enough propellant to reach low Earth orbit, but it doesn't have enough propellant to go to Mars, not even close. The journey to Mars requires a significant velocity change, what engineers call delta V. You need to accelerate out of Earth orbit, cruise to Mars, and then decelerate to enter Martian orbit or land on the surface. All of that requires fuel, a lot of fuel. More fuel than a single Starship can carry, while also carrying a crew and their supplies. So SpaceX's solution is orbital refueling. The concept works like this. First, you launch a Starship to low Earth orbit. This Starship is your crew vehicle. It arrives in orbit with mostly empty propellant tanks. Then, you launch a series of tanker Starships, identical vehicles, but configured to carry only propellant, no crew. Each tanker docks with the crew vehicle and transfers fuel, one tanker after another, slowly filling the crew vehicle's tanks. Estimates suggest it will take somewhere between 8 and 16 tanker flights to fully refuel a single Starship in orbit, depending on the mission profile and payload mass. Once the crew vehicle is fully fueled, it can depart for Mars. This approach, multiple launches to support a single mission, is fundamentally different from how we've done space exploration before. It's more complex. It requires many successful launches in a short period of time. It requires precise orbital mechanics and docking operations. But it's also the only way to get enough fuel to Mars without building an impossibly large rocket. The challenge now is proving that it works. Refueling a spacecraft in orbit has never been done before, not by anyone, not at this scale. SpaceX is currently developing the technology, and a demonstration is planned for the near future. But until it's tested in space, it remains unproven. Once the Starship leaves Earth orbit, it enters deep space, and deep space is hostile. Outside Earth's protective magnetosphere, the crew is exposed to two primary sources of radiation: galactic cosmic rays and solar particle events. Galactic cosmic rays are high-energy particles originating from outside our solar system. They consist mostly of protons, but also include heavier ions like iron and carbon. These particles are traveling at nearly the speed of light and can penetrate deep into matter, including human tissue. The estimated radiation dose for a 3-year Mars mission is approximately 900 millisieverts. That's roughly 300 times the average annual radiation dose on Earth. Exposure at this level significantly increases the risk of cancer. It also increases the risk of cardiovascular disease, cataracts, and cognitive decline. Animal studies show that exposure to high-energy particles causes changes in brain structure. Neurons lose dendritic complexity. Synaptic density decreases. Memory and decision-making are impaired. Some researchers estimate that 1 in 5 astronauts on a long-duration Mars mission would experience measurable cognitive decline. Solar particle events are different. These are bursts of radiation released during solar flares and coronal mass ejections. They consist mostly of lower-energy protons, but they come in enormous quantities. A large solar particle event can deliver a lethal radiation dose in a matter of hours if the crew is unprotected. The good news is that solar particle events are somewhat predictable. They occur more frequently during solar maximum, and monitoring systems can provide some warning. The bad news is that no amount of warning helps if you don't have adequate shielding. Traditional shielding materials like lead or aluminum are heavy and not particularly effective against high-energy particles. In fact, when high-energy particles strike heavy materials, they can produce secondary radiation that's even more dangerous than the original particles. So current research focuses on lightweight shielding materials with high hydrogen content, things like water, polyethylene, or advanced materials like hydrogenated boron nitride nanotubes. These materials are better at absorbing radiation without producing harmful secondary particles. The Starship design includes some radiation protection, but it's unclear whether it will be enough for a Mars mission. Additional shielding may need to be added, increasing the vehicle's mass. Another option is to use supplies as shielding. Water, food, and equipment could be arranged around sleeping quarters to create a radiation shelter. But even with shielding, the crew will still receive a significant dose. NASA's current career exposure limits for astronauts allow for a 3% increase in lifetime cancer risk. A Mars mission would exceed those limits. So the question becomes, is the risk acceptable? There's no easy answer. Getting to Mars is one thing. Landing on Mars is something else entirely. The challenge is the Martian atmosphere. It's thick enough to cause heating and drag during entry, but not thick enough to slow a spacecraft down for landing. On Earth, parachutes work well because the atmosphere is dense. On Mars, the atmosphere has less than 1% the density of Earth's. A parachute can help, but it's not enough. Previous Mars landers and rovers have used a combination of heat shields, parachutes, and retrorockets to land safely. But all of those vehicles were relatively small, roughly 1 metric ton at most. Starship has a mass of approximately 100 metric tons when empty, and significantly more when carrying crew and cargo. That's 100 times heavier than anything we've ever landed on Mars. The thin atmosphere cannot slow it down sufficiently through aerodynamic drag alone, so the spacecraft must use its engines to decelerate. This is called supersonic retropropulsion. The spacecraft fires its engines while traveling at supersonic speeds through the atmosphere, creating thrust in the direction of travel to slow down. Until recently, engineers weren't sure this would work. Firing engines backwards while moving through an atmosphere at high speed creates a shockwave that moves unpredictably. It could potentially damage or destabilize the vehicle. But SpaceX has been testing supersonic retropropulsion with its Falcon 9 rocket boosters, which use the same technique to return to Earth and land vertically after launching payloads to orbit. Those tests have been successful. The data shows that the shock wave actually forms a protective bubble around the vehicle, insulating it from buffeting and reducing heating. This is promising. It suggests that supersonic retropropulsion at Mars is feasible. But there are still challenges. Mars has unpredictable winds and dust storms. Landing accuracy is critical. The vehicle needs to land on relatively flat terrain, free of large rocks or slopes that could tip it over. Current technologies can land a spacecraft within an ellipse of about 20 kilometers. That's good, but not good enough for a crewed mission where the landing site must be carefully chosen. So new navigation technologies are being developed. These include terrain relative navigation, which uses cameras and sensors to identify landmarks during descent and adjust the trajectory in real time. The goal is to land within a few hundred meters of the target. Even with perfect navigation, the landing itself is risky. The engines must fire at precisely the right time. Too early, and the spacecraft runs out of fuel before reaching the ground. Too late, and it crashes. The margins are razor thin. Once on the surface, the crew faces a new set of challenges. Mars is cold. Surface temperatures range from about -125 degrees Celsius at the poles during winter to 20 degrees Celsius near the equator during summer. The average temperature is around -60 degrees Celsius. The atmosphere is mostly carbon dioxide with traces of nitrogen and argon. There's no oxygen. The atmospheric pressure is less than 1% of Earth's. A human exposed to the Martian environment would lose consciousness within 15 seconds and die within 90 seconds. So the crew needs a habitat, a pressurized environment where they can live and work. Early concepts involve landing a habitat module ahead of the crew. This module would deploy automatically, inflate or unfold, and prepare itself for habitation. The habitat must provide everything the crew needs: breathable air, drinkable water, food, temperature control, radiation shielding, and waste processing. It must also be reliable. There's no emergency rescue, no resupply missions. If something breaks, the crew has to fix it themselves. That's a daunting requirement. One way to reduce risk is to use local resources. This is called in-situ resource utilization, or ISRU. Mars has resources that can be harvested and processed to support the crew. The atmosphere is mostly carbon dioxide. That CO2 can be captured and processed to produce oxygen for breathing and methane for fuel. Water ice exists on Mars, buried beneath the surface in many regions. If the crew can access it, they can melt it, purify it, and use it for drinking, hygiene, and agriculture. The soil contains minerals that could be used for construction or manufacturing. But harvesting these resources requires equipment, drills, excavators, chemical processing plants, power systems. All of this must be designed, tested, and transported to Mars. And it all must work reliably in an environment where temperatures swing wildly, dust storms are common, and there's no one to call for help. NASA is currently developing ISRU technologies. A small experiment called MOXIE was sent to Mars aboard the Perseverance rover in 2021. MOXIE demonstrated that oxygen can be produced from the Martian atmosphere. It successfully converted carbon dioxide into oxygen multiple times, proving the basic concept works. A scaled-up version of MOXIE could produce enough oxygen to support a crew and provide propellant for a return vehicle. But scaling up is not trivial. A full-scale system would need to produce approximately 25 tons of oxygen over the course of a year and a half. That requires a lot of power and robust equipment. Here's the critical issue. The crew needs a way to get home. That means they need a rocket on Mars, fueled and ready to launch by the time they're ready to leave. Carrying all that propellant from Earth is not realistic. The mass requirements are too high. So, the propellant must be produced on Mars. The most commonly proposed approach is to produce methane and oxygen from Martian resources. The process works like this. First, you capture carbon dioxide from the atmosphere. Then you react it with hydrogen to produce methane and water. This reaction is called the Sabatier process. The water is then electrolyzed to produce hydrogen and oxygen. The hydrogen is recycled back into the Sabatier reactor. The oxygen is stored as propellant. The methane produced by the Sabatier process is also stored as propellant. If you have a source of water on Mars, the process becomes simpler. You can electrolyze the water directly to produce hydrogen and oxygen, then use the hydrogen to drive the Sabatier reaction. But this requires infrastructure: chemical reactors, electrolyzers, compressors, cryogenic storage tanks, and all of it needs power, a lot of power. Current estimates suggest that producing enough propellant for a Mars ascent vehicle will require a power system capable of generating several hundred kilowatts continuously over a period of 500 days. That's far more power than any spacecraft has ever produced. So what's the power source? Two main options are being considered: solar panels and nuclear reactors. Solar power is appealing because it's proven technology. Photovoltaic panels are lightweight, reliable, and don't require complex machinery. But Mars is farther from the Sun than Earth, so solar panels produce less power. They're also affected by dust, which accumulates on the panels and reduces efficiency. A recent analysis suggests that for landing sites near the Martian equator, solar power could be viable, especially if supplemented with hydrogen fuel cells for nighttime power. But at higher latitudes, where sunlight is weaker and dust storms are more frequent, nuclear power may be necessary. NASA has been developing small nuclear reactors called kilopower units. These reactors use uranium fission to generate heat, which is then converted into electricity. A single kilopower unit can produce about 10 kilowatts continuously, day or night, regardless of weather. For a Mars mission, several kilopower units could be linked together to provide the necessary power. The challenge is mass. Nuclear reactors are heavy, and so is the shielding required to protect the crew from radiation. But they're also reliable. And on Mars, reliability matters more than efficiency. The crew needs to eat. A human requires approximately 2,000 to 2,500 calories per day, depending on activity level. Over the course of a 900-day mission, each crew member will need roughly 2 million calories. That's a lot of food. Pre-packaged meals from Earth could work, but they take up space and add mass. And after a year or two, the crew will be desperate for variety. So researchers are developing ways to grow food on Mars. The concept is called bioregenerative life support. Instead of relying entirely on stored food, the crew cultivates crops inside a pressurized greenhouse. The plants consume carbon dioxide and produce oxygen, helping to maintain the habitat's atmosphere. They also provide fresh food, which improves morale and nutrition. Experiments aboard the International Space Station have shown that plants can grow in microgravity. They've successfully grown lettuce, radishes, and tomatoes in space. Mars has gravity about 38% of Earth's, so growing plants there should be easier. But there are challenges. Martian soil contains perchlorates, toxic compounds that must be removed before the soil can be used for agriculture. The soil also lacks organic matter and beneficial microbes. So the crew will need to either import soil from Earth or process Martian soil to make it safe and fertile. They'll also need light. Mars receives less sunlight than Earth, and the greenhouse may need supplemental lighting, especially during winter or dust storms. And they'll need water. Growing food requires a lot of water. The crew will need to recycle water efficiently, capturing moisture from the air and waste and using it to irrigate crops. It's a complex system, but if it works, it could significantly reduce the mass of supplies that need to be brought from Earth. Let's talk about the hardest part of going to Mars. It's not the engineering, it's not the radiation, it's not the propellant production or the landing, it's the people. A Mars mission will push human psychology to its limits. The crew will be confined in a small spacecraft for months, with the same people, in a dangerous environment, far from home. They'll experience isolation, monotony, and stress. They'll miss their families. They'll have no privacy. Interpersonal conflicts will arise. And when conflicts arise, there's no escape. No therapist to call, no way to take a break. The crew must resolve problems themselves. Studies of long-duration missions on the International Space Station and in ground-based isolation simulations have identified several psychological risks. One is depression. Crew members report feelings of sadness, fatigue, and low motivation. Some experience sleep disturbances. Another is interpersonal tension. Small annoyances can escalate into serious conflicts when there's no way to avoid each other. A third is cognitive decline. Stress, sleep deprivation, and radiation exposure can all impair memory, attention, and decision-making. NASA has developed psychological support systems to mitigate these risks. Crew members receive training in conflict resolution and stress management. They have regular private conferences with ground-based counselors. They receive care packages and surprise messages from loved ones. But on a Mars mission, communication delays change everything. Radio signals take between 4 and 24 minutes to travel between Earth and Mars, depending on the planet's positions. A conversation becomes impossible. If a crew member is struggling emotionally, they can't just call home and talk to someone in real time. They send a message and wait. The response arrives half an hour later. That delay creates a sense of profound isolation. So researchers are developing tools to help the crew support each other. One is a computer-based therapy program that guides crew members through problem-solving exercises and cognitive behavioral techniques. Another is a cognitive assessment tool that crew members can use to monitor their own mental state, similar to checking blood pressure. But ultimately, the success of the mission depends on the people. Choosing the right crew individuals who are resilient, adaptable, and compatible is critical. So when will all of this happen? SpaceX founder Elon Musk has said that the first uncrewed Starship mission to Mars could launch as early as 2026 during the next favorable launch window. The goal would be to land the spacecraft safely, test systems, and demonstrate that the technology works. If that mission succeeds, the next window in 2028 could see additional cargo missions delivering supplies, equipment, and infrastructure. And then, perhaps in 2030 or 2032, the first crewed mission could launch. These timelines are ambitious, extremely ambitious. Many experts believe they're unrealistic. Building, testing, and certifying all the required systems will take time. Delays are inevitable. But even if the timeline slips by a decade, we're still talking about sending humans to Mars within the next 20 years. That's extraordinary. So here's what we know. Going to Mars is possible. The technology exists or is being developed. We know how to build the rocket. Starship is flying, and each test brings it closer to operational status. We know how to navigate to Mars. The orbital mechanics are well understood. We've sent dozens of robotic missions. We know how to land. Supersonic retropropulsion works. It needs refinement, but the fundamentals are sound. We know how to produce oxygen and propellant from Martian resources. MOXIE has demonstrated the concept. Scaling it up is an engineering challenge, not a scientific one. We know how to protect the crew from radiation, at least partially. Shielding materials are improving. Medical countermeasures are being researched. We know how to grow food in space. Experiments on the ISS have proven it's possible. What we don't know is whether we can put all of these pieces together into a reliable, safe, integrated system, and we won't know until we try. That's the nature of exploration. You gather the best information available. You build the best systems you can. You test them rigorously, and then you go. The first crew to Mars will be stepping into the unknown. They will face dangers we can anticipate and dangers we cannot. They will be alone, millions of miles from home, in an environment that has never supported human life. And if something goes wrong, there is no rescue, no quick return. They will have to solve the problem themselves, or they will not come home. It's a daunting prospect, but it's also the most ambitious thing humanity has ever attempted. And the fact that we're even having this conversation, that we're seriously planning missions, building hardware, testing technologies, is remarkable. A century ago, the idea of flying to the moon was pure fantasy. 50 years ago, we did it. Now we're turning our attention to the next horizon. Mars is not a fantasy, it's a destination. The question is no longer whether we can go. The question is when, and how well we prepare. There's something profound about standing on Earth and looking up at Mars in the night sky. That red dot has been there for as long as humans have had eyes to see. Ancient civilizations tracked its movements. They built myths around it. They wondered what it was. Now we know it's a planet, a world, a place. And soon, it will be a place where humans have walked. The journey to Mars is not just about technology. It's about what we're capable of as a species. It's about choosing to reach beyond what's comfortable and familiar, to accept risk in pursuit of discovery. The crew who makes that first journey will endure hardships we can barely imagine. Isolation, danger, uncertainty. But they will also experience something no human has ever experienced before. They will see Earth as a distant blue dot, fading in the blackness. They will watch Mars grow larger day by day, until finally they descend through its thin atmosphere and touch its surface. They will be the first, but they won't be the last. If the first mission succeeds, others will follow. Habitats will grow. Infrastructure will expand. Eventually, Mars may become a second home for humanity, or it may not. We don't know what we'll find there. We don't know what challenges we'll face, but we know we have to try, because the alternative is to stay here, on this one planet, forever. And that's not who we are. We are explorers. We always have been, and Mars is calling.